of these webinars. And let's get to work. This is just one page I put to show my background. I work as far as research and design in both bridges and buildings. On the left, you can see my bridge projects. I'm very interested in long span bridges, either research, inspection. I've been involved in as design team. And on the right, you can see my building projects. My most important project, of course, was investigation of collapse of World Trade Center, the tragic event for the National Science Foundation. I went there after 1 week after, and that's also part of one of ethics webinars. I give ethics webinars almost every month, and some of these projects here, Bay Bridge and other projects, are monthly webinar. With that, this is the day of launch of Shuttle, which exploded 73 seconds after the liftoff. And everything was fine until almost 70 seconds, and suddenly it exploded and disintegrated. Everything looks fine. At this point, when it goes, everything looks normal until it's not. This is the problem. Tragically, 7 astronauts lost their lives in this tragedy. Take a moment remembering them. What we are going to do is first, we are going to talk about technical causes of the Challenger failure from engineering point of view. Then the decision process before launch that really was at the root of this tragedy. And then National Society of Professional Engineers Code of Ethics, how it applies, and we'll look into the decisions that were made from day one. Even before first launch was done, there were decisions that violated the National Code of Ethics, and those decisions were at the root of this tragic event. Practical tools. We have some discussion of what we can do as professional engineers. I've been also, like you, practicing structural engineering for some time. Now is 15 some years. And preparing these webinars, I put myself in your place. especially the ones that are not in my area. I spend usually for these kind of like shuttle aerospace is not my field. I'm in civil engineering, structural engineering, so forth. I spend more, maybe 300 for 400 hours for each, because I put myself in your place. I have heard about this. I know a little bit. Of course, I'm an engineer. I'm very curious, and I can understand even aerospace. So I put it that way. And then I always in these webinars feel that what would I do? What can I do, even if I am in that situation that engineers in this case were? And you'll see later that engineers really were heroes. Engineers were trying to stop this. They knew it was going to happen, and managers overruled them. Sounds familiar, right? Many of you might have seen this, especially junior ones. It's a really difficult problem in engineering firms and entities that the boss wants something that's impossible to deliver, or we are going to violate the code of ethics or your morality, but still it happens. So my team was really to show how we can hold safety paramount. That's really the title of my talk. And all my life, I'm sure all of you do the same thing. It's just lives are the most important thing in this planet. With that, let's look at the system and the seeds of failure that were planted from day one, as I mentioned. So after we do that, we'll get into ethics. So right now, let's focus on engineering. Space Shuttle had three main segments, components. They were integrated, making a system called Space Shuttle. The most important one, of course, that was returning back to Earth was the orbiter, which also sometimes it was called Space Shuttle. They meant orbiter, the one that is coming back. The second one was really rockets, two rockets, solid rocket boosters. They had solid fuel, and of course, during flight, it will turn into high pressurized gas, and they will providing 80% of the lift thrust. The other 20% was coming from the three engines of the orbiter, and the fuel for those three engines of the orbiter, oxygen and hydrogen, was coming from the external tank, which had two separate oxygen and hydrogen tanks inside. And as the liftoff was continuing, they will mix the oxygen and hydrogen will be mixed and fed into the engines, and the shuttle will go up. All this fuel, either rocket booster, solid rocket booster, or the external tank giving fuel to three engines, it was all for only 2 minutes of uplift until the shuttle gets into the orbit. And then that was the fuel was done. The solid rocket booster will come back after it's empty, and it will be recovered and will be reused. But the external tank was dropped in the ocean and was lost. That's why you can see it's not even painted. So with that, the failure was not in the orbiter, actually. The failure was in the rocket booster, this one on the right side, at the base of it, behind this wing. And we're going to focus on that. So our focus from now on will be on a rocket booster, a solid rocket booster, and the joints, these joints. you have heard O-rings. You're gonna hear maybe another 200 times during this presentation. But that is really one joint that caused the whole system disintegrate. We, the structural engineer, call this fracture critical. Fracture critical system is a system that failure of one element will cause significant partial or full collapse of the structure. This was certainly fracture critical because, as the tragedy showed, failure of one joint, one small joint, probably not more than $2,000 worth, failed the entire system. The reusable solid rocket booster had these segments, and you might say why they built this in segments, because the rocket booster was manufactured in Utah by a company called Thiokol, which later became Morton Thiokol. In this webinar, just to save time, a few seconds probably, but I'll call it just Thiokol, the company that was a contractor to design and build this booster. And because it was in Utah, then segments were separated, put on the train, and then it was sent to where it was assembled, and from there it was basically put on the launch pad and connected to the external tank and so forth. So these field joints had these O-rings, and there were two of them. One was called primary, and the other one was secondary. When I show you the joint detail, you'll see that the primary is the first one that is exposed to air, and the secondary is behind it, of course, secondary. And then the problem was really here, and the problem was, can you imagine just the failure of this primary O-ring, one O-ring? I don't know, it might be like $200 worth at the time, I guess. Then there were two of these O-rings in each joint, and the redundancy, of course, they put two to say that they are redundant. If the primary phase burns out, these are rubber, the other one will keep. Why did they have these O-rings, these rubber rings? Because the fuel inside during the flight will turn into high pressurized gas, and that gas can get out of the joint, the field joint, right? So you needed something to stop the gas from coming out. In this case, of course, you'll see later, jumping a little ahead, you'll see that the primary O-ring in one joint only failed to stop the gas from coming out. The gas came out, and then it became fuel, and then started melting the skin of the external tank, and of course it's hydrogen oxygen. It exploded and disintegrated the whole system. But the ductility, these primary and secondary were not equal. It depended. If the primary went, it's not like secondary takes place and steps in. They work together. And in this case, of course, both of them kind of primary going, secondary also went. It didn't work the way they thought. Now, this is important because this is showing the joints. See, this joint is here. These are like segments. You can see these segments. And if you look at cross section, it's kind of cross section, the cylinder. The middle is empty for air to get in and do the gas. The solid fuel turns into gas. So when that was happening, there was a very high pressure inside, and that high pressure bent the cylinder, right, between the two joints, because these two joints are kind of like a stiff. You can see the detail close up. This green is the pin. So they will bring the top portion and the tank and put it in the clevis and pass the pin, and then the connection will be done. But because of this is very important. Because of the bending of the cylinder, the joint will open. You can see this part. But the O-rings were designed such that if it opens, they expand and they fill up the gaps so the gas does not come out. So let's look at close-up. This is the joint. It's called O-ring joint. You can see primary O-ring. You can see secondary O-ring. They were round, right? These are just rubber rings. They were round, about quarter of an inch, to give you some idea. So what happened was when they were putting in and everything was being manufactured, before those gases are generated during the launch, before the launch started, it's a solid fuel, so it's just sitting there, and this is the situation of the tank and clevis. So by the way, the left side is inside, and the right side is outside. So all is good. So when it's manufactured and joint is created, then it is compressed. This quarter of an inch rubber ring, O-ring, compressed and seals the place. There's some putty and other paste to help, but basically the O-ring is responsible for sealing the joint so the gas doesn't go from left side inside and go out. So, but what happens is when that expansion happens, it's not uniform. It's not expanding at the joint. It's expanding at mid-level of the cylinder. So this happens. It opens up. But that's fine. That's the design. So the oval flexible rubber, right, O-ring expands and seals. So all is good. As far as the O-ring stays flexible, stays rubber, and does what rubber does, expand from oval to circle again, quarter an inch, and seal the joint. So let's see what happened. What happened was that the temperature plays a role. We'll get to that in more detail. But I tell you, because there is this 53 degrees mentioned, that's going to be an important number. 53 degrees was the lowest temperature that any shuttle was launched. And you know that rubber gets kind of like rigid if you put it inside ice bucket. Rubber is flexible if it is warm and nice. So this 53 degrees will play a major role, very major role, and you'll see what happens. Because when they launch the shuttle, the Challenger temperature was very cold, colder than this 53 degree, and that is really the whole issue of ethics. Let me tell you, not to keep you in suspense, engineers were saying that we should not launch because engineers who were in charge of O-rings, they were saying, great heroes, they were saying that we should not launch. We know that we have only had launch down to 53 degrees weather. We never had launch at 26 degrees. And the managers said no. We are going to just ignore you. We're going to go ahead and launch it. What are you talking about? President Reagan is watching. The whole many schools, students, especially elementary schools, are watching for teacher McCullough. So they just overruled engineers, and they went ahead and launched, and that's what exactly happened as engineers were saying. This is actually one of the webinars I like very much. Not the tragic situation is not something that I can say I like it, but I like the way engineers act. So heroically tried to stop managers. Of course, they failed, and the whole system. So the core was O-rings responsible. And the reason O-rings did not behave the way they should have is because it was cold plate. So this is showing the test. Each dot is a test. So horizontal axis is temperature in Fahrenheit. So the green dots or blue dots here are flights launched during high temperature and no damage. The vertical axis is the total O-ring damage. Right? There are a lot of O-rings, about 20, 30 O-rings in the whole system, and this shows how many of them damaged. If you look at it, when temperature was very high, about kind of like 65 degrees, there was almost no damage to O-rings. When you went to lower temperature, you can see maybe 2, 3 of them. You go to 53. This is that 53 degree that is kind of like the lowest. It had 66 O-rings damaged. Now this one you can say that, oh, this is 75. Why did it have 4? But basically the damage in this case was not O-ring. Around the O-ring there's paste, there is other things, and if they burn or they are not installed properly, you can get damage. So this is not really is because of low temperature. This is something else. But if you consider the rest of them, this is what happened. So the launch on January 28th happened at very low temperatures here, 36 degrees. The prediction was 26 even, but they waited until 11 o'clock, didn't launch at 9, gets warmer, but still it was 36 degrees. So very low temperature. The problem is that this problem of damage gradually became accepted practice, that no one was worried that, like 6 O-rings, which are really not determined, not redundant system, even though they thought 2 O-rings are redundant. But failure of one joint, as I mentioned, fracture critical system, you're done. The whole system will fail. But they were just, fine, it's life. Two rings, O-rings damage for $1 billion system, that's okay. We'll do something about it. Or we don't, which they didn't actually. They just continue accepting the damage. Now, these are some pictures from the day of launch, the morning of January 28th, 1986. Almost exactly 40 years and 2 weeks, something like that. So you can see the rocket booster on the left photo, and this is from the launch pad and other facility, and you can see the night before there was rain, and you can see the ice. Here is some equipment that they had at the launch pad to measure things, and you can see this instrumentation, control is buried under ice almost. And this is, of course, the rocket booster. And then you can see it is closed. You can see this whole ice and snow. So if you are the person in charge of launch, you could just walk there and see the ice and realize what engineers are talking about. But they didn't. So what they did was they launched at 36 degrees. This is 15 degrees before, less than what we have, right? So what happened? I made it blue, the color, because really the O-rings were frozen like ice, no longer red, flexible. So what happened was, this is the original, right? And you have assembled, and it's sitting there before the launch. The solid rocket has only solid fuel, right? And as soon as you start ignition, the gas pressure bends the cylinder opens up, and the O-ring, which is frozen, this is ours. It's not expanding. It's not getting back to round quarter an inch, right? So what happened? Very simple physics at work. So because it stayed open, the gas, remember always left side is the gas in my pictures. I made sure all pictures are consistent, all photos and drawings. So the high pressure hot gas is coming out. This is very, very serious gas. It can burn very fast. It comes out, and of course, it starts burning. And if you remember the picture of Shuttle, next door is just the skin of the external tank, which behind it is the oxygen tank, and the oxygen tank is hydrogen tank, and it's just a bomb. It's really, Shuttle was riding on a bomb, and then the two smaller bombs on the side, holding two smaller bombs. This is just amazingly dangerous system. But that's the way rockets and space travel is even today. So then there were more problems. The problem was that actually the night before, when the rain came, the water, now the right side is of course outside. I put the raindrops there. So the raindrops come in and filled up this little gap and went behind the secondary O-ring. And of course, the secondary O-ring is now very cold too. So that also, when after the failure, of course, there were a lot of tests, and then they understood that the joint was even worse than they thought because of this ice just next to the O-rings. Now, the last straw, like breaking the back of the camel, the last straw, what it was. During the launch, because the weather was very turbulent that week, during the launch, for a full 20 seconds, as the shuttle started going up, I got this picture of wind shear, and I mounted on it with my very limited talents of graphics, mounted the shuttle. But basically, wind shear is when you have a horizontal wind going in various directions, like these arrows. And for 20 seconds, there were very significant horizontal wind force on the shuttle in various directions. So it creates torsion. As it goes through it, at one point it's from the left, at one point go up, it's from the right. So it starts rotating the shuttle and also putting a lot of dynamic pressure on. So there were no instrumentation really, unfortunately. I was so surprised to see that for a machine of this expense and this complexity, they had very little instrumentation, few strain gauges here and there. So we don't know exactly what went on during those 20 seconds, but that windshield creates vibration, and that vibration creates uh, it is understood that probably the reason this is last straw because the O-rings and the putty, in fact, it is understood now that initially when the gas started coming out, the putty and others got melted and sealed the joint, actually. The O-ring also got a little warmer and sealed. But then, in fact, the smoke was coming out. The video later showed that the smoke is coming out from the O-ring joint at the bottom on the launch pad. So as soon as they turned on the engines, it was there. But after a few seconds, it stopped. The smoke stops. And then near the 70 seconds, just few seconds before the explosion, the fume is coming out. It's assumed that this last straw, I call it last straw, it's assumed that this last straw actually, the vibration kind of like crushed those elements that were blocking the hole between the rubber and the side, the tank, and then the gas started coming out. It's clear. So this last straw was windshield. Then after failure, President Reagan appointed a very high caliber commission. Richard Feynman, the Nobel Prize winner physicist, if you know him, I've read, I think, 3 of his books. He was a character. He could do opening the locks without the key. This is Nobel Prize winner, but he was extremely talented and genius. So he was appointed the committee and astronauts and, of course, others knowledgeable experts in this kind of thing. So they went through it for a couple of months, 3-4 months, and came up with the 4-volume, very, very interesting report. I always say that the reports of National Transportation Safety Board and instruction in bridge engineering are just the model for what an investigation failure analysis report should be. And in fact, the report of this presidential commissions, one for this one and one, unfortunately, also Columbia Shuttle paid in return to Earth. These are really, I think, the highest standards of failure analysis and report writing. And I've used a lot of information from that package of 4 volumes in this webinar. So the failure, the commission after those studies attributed the failure to vulnerabilities that the solid rocket booster field joint design had, and that those vulnerabilities made O-ring performance sensitive to low temperatures. That does it. And engineers were screaming that don't launch, the weather is cold. They knew their job, right? That's the minimum expectation of us, right? We know what we are doing. At least we know that particular design that's on my desk now these days on your laptop screen or computer screen. And that ended up really the O-ring not performing, the rubber not being flexible and in low temperature, causing this disaster. So it's interesting. Actually, the original contract or proposal, Thiokol had a proposal, And in that proposal, the O-ring joint was what you see on the left. Kind of like there was one O-ring in vertical surface and one O-ring in the horizontal surface. So this was the one that went into proposal. And of course, there were 2, 3 other companies like Thiokol, aerospace companies. They were also proposing, and Thiokol won the contract by having the one on the left. But after they got the contract, they changed. They changed to the one that's on the right, and I called it as-built design. The one on the left, I called original design. And then it was very interesting. The Thiokol and NASA Marshall Center is where the shuttle is launched and put together, boosted together. So they actually liked the proposal, and they gave the contract to Thiokol, right? This detail on the left. But after contract was given, they liked the change to the right one, which failed, of course, miserably. And they said that the change was because of what? To make manufacturing simple, that's for sure. But this red line, oh my God, to reduce the cost. Think about it. NASA, having 7 astronauts and billions of dollars put in this project, and is saying that this saved how much? I couldn't find the numbers. I cannot imagine more than a few $1 million altogether, going from the one on the left to the one on the right. Of course, the one on the left was also not right, not correct. But NASA didn't know it at the time. NASA just said that NASA thought actually the one on the left is very good, and it praised actually the contract, that the reason we gave this contract to Thiokol because there was a lot of criticism. Some companies were thinking that the proposal was not as good, and the committee that the head of committee that was selection committee had said on those days, a few weeks after the contract was given to Thiokol, that one of the reasons that we gave contract to Thiokol with this left detail is actually this detail. NASA cited this detail on the left as being the reason, one of the reasons they gave to Thiokol. After contract, when Thiokol changed it to the right one, they just kind of said, this is the cost. This I will come back because this is ethics issue. This is not just giving you the engineering. You'll see there are really serious issues here. The reason actually it would not work, the design that was in the proposal is this. If you have one O-ring in the vertical surface and one O-ring in the horizontal surface, what will happen is when the gases start building up and pressure on the left side is pushing the tank to the right, you will end up with opening both, right? Because this change of angle happens. It doesn't go horizontal. It rotates, and the rotation opens not only the primary or secondary, even it's not clear which one is primary, which one is second. They're just 2 O-rings, one in horizontal surface, one on the vertical surface, and both of them open up. So that's not going to work. In fact, one thing I realized was that I do quite a lot of work in connections, steel connections of bridges and buildings. The slide I showed, a lot of work that I did as faculty at UC was test connections, steel, some concrete, even some composite, and develop design guidelines for codes and specifications. So I like really looking at design of connections and joints. I had a colleague, Professor Scordeles. Some of you might know him. He's passed away now. And one day we were talking, and he was saying, "Look, connection." He was very senior, and I was young assistant professor. He was saying, "Look, connections, structures are just elements that are fine. We know everything about them. They don't fade. What fades, they are elements separated. The connections are the critical elements." Yeah, sorry. He put it this way. Connections are really the critical elements that you should look into and design properly. The members, the beams, the columns are just keeping connections away. Look at it that way. So when I looked at it, I realized actually this is not buildable, this detail, because it basically doesn't have a tolerance. Let me go back there. Uh, when you assemble it, if this surface is not exactly the same place as this one, even temperature can change that. Then this pin cannot go in. You cannot align the pinhole, which was very small, 1/64 of an inch, just gap. That tolerance cannot be done here. So you bring the top part in and put it in, and this stops here, and you see that the pin cannot get in. So that had a major problem. Maybe that's why they decided to change it. In any event, so what happened was, of course, after tragedy, still space shuttle program continued, although it stopped for a year or two, and almost $10 million were spent to change it. And after the disaster, it was changed to this, which really had three joints, and if the gases push this and there was separation, apparently it will not do this. So this is the old as-built connection that because of gas bending it, this opens. But in this case, you see there is this third O-ring, but more importantly, the whole thing is kind of like one integral part, and there is no separation. This continued for a couple of years until the whole, I mean, it was 86, 2011. It's like, what was that? Like 20 years. And then the whole thing stopped. So the details of launch on January 28th and failure is here. So let me show this. It runs again. You can, if you look carefully, there's the plume of the, here you can see. Let me stop it. There is a plume that in this video you can see coming up of the base. And of course, that explodes the tank and the whole thing. And this is one of the boosters going. There is the shuttle orbiter and so forth. So what happened was at the end, when it was 73 seconds into flight, it just exploded. But the most tragic thing was that the engineers had expressed concern that the O-rings will not survive this cold temperature. They cannot seal. The forecast for launch day was 26. They waited until it was 36, around 11:30. The vice president was watching, actually, not President Reagan, but Vice President Bush was watching. Bush the father and all the school kids and teachers, the whole country was very much watching the teachers, the college go up. So this is the event. So the question is not really what failed. we know what we understand. I tried to bring it to you as clearly as I could with the time that I had. But the question is, why the launch was approved with so much knowledge that engineers had and years of experience with O-ring failure, even before the shuttle, any shuttle went to orbit, they had the first shuttle was just under the orbit for testing. They could see the damage to O-ring. The year was 1977. 1977, still we had no shuttle going up. And the shuttle that was going Endeavour below the orbit is defined as 100 kilometers above the ground surface. So anytime it went up for testing, the O-rings were getting damaged. 1977. So why, with the knowledge of cold weather causing rubber to get stiff and brittle, was approved. And that's what we're going to address in the next section. So the selection of tackle had some strange looking, at least. I'm not going to say unethical, but strange looking activity that raised a lot of eyebrows and direct criticism of selection process by other companies, by competitors who were also submitting proposals. So in 1973, Paracal got the contract for building boosters. That was the only contract they had. The other parts were other companies. So costs were the main concern. I mentioned this before, but still, it amazes me that the government agency that is using taxpayers' money, that is using those astronauts' money, is not concerned about safety of those astronauts. It's mind-boggling. So, as I mentioned before, in December 73, after they gave, 1 month after they gave the contract to Paracal, they said that, cost advantages were substantial and consistent throughout all areas evaluated. They're looking at all these various components of this most complex machine that actually it's said. Space shuttle was the most complex machine built by human beings. There's more than 1 million pieces in it, the components. So for something like that, you are looking at every area for cost saving, including the connection area, right? So why did this happen? Let's look at the NASA budget. Why NASA, which gets the budget from Congress, was so concerned at the time. This is the budget in terms of billions on the left vertical axis, adjusted for inflation. And horizontal axis is the years. So starting with 1959, kind of like when a few years after NASA was kind of like formed out of another agency, which used to be called NACA, if I'm not mistaken. But in any event, what happened was, here was President Kennedy's speech. We have to go to moon by before the end of this decade. So by 19 70. In other words, if I remember it, he said in a decade, which meant by 1969 we should have man on the moon. So that's one event there. Then it goes up, of course, 35, 40 billion. Then 1967, first Apollo mission, not landing on the moon yet. Then 69, of course, mission accomplished. 10 years after President Kennedy's speech. What happens? We have first moon landing. Then 72, last moon landing. So it was only 3 years that those, I think there were what, total of 11 moon landings, if I'm not mistaken. Then, as the moon landing stopped, now NASA moved into reusable orbit transportation. At the time, the space station was in the planning, and the idea was that we need a shuttle to take load and people from Earth to that space station and back, and all kind of other things. Carry the satellites and place them in orbit and above orbit and so forth. So Tycho got a contract for solid rocket boosters in 73. But you can see the budget is really going down. That's why NASA was concerned about budget. But they shouldn't have been concerned about budget before they were concerned about safety. In other words, you can't put budget before safety, right? Safety is paramount. That's the first canon of code of ethics. So then the whole shuttle program is going on, and then in 1986, the shuttle Challenger explodes, and then in 2003, Columbia explodes. The kind of re-entry disintegrates. This is during the launch. This is the re-entry. These are the two most critical parts. In between, really, shuttle is just gliding and just going without any engine in the orbit and so forth. What is critical is launch, and what's critical is return, breaking through atmosphere and coming to land. So in both cases, of course, the design failed. And in 2011, the whole program ended. And that is the story of this failure from engineering point of view. The question that's very important I mentioned is what? The question is why the launch in freezing temperature, why it was approved. Then I want to show you how much NASA and Toyota knew about how O-rings will perform under low temperature. Why managers, NASA managers, and fire call managers overruled engineers and did this? Many of you, I'm sure, I have had, and many of you might have had experience, not as dramatic as this one, and fortunately not as tragic as this, but in small things, you have had experience that your client sometimes, who's not engineer, and sometimes even your supervisors say something that you should do, and both of you know that this is wrong. It's not going to work, but somehow there are constraints around it. The drawings should be sent out by end of February. You got to get this moving, that, right? The concrete has to be poured. The concrete truck is right standing by you, and you call your boss and say that, look, the temperature is very, very cold here. There's ice on the inside the forms. And so we can't wait. The concrete gets hardened inside the truck, right? So then let's see what happens. So here is the approval process or flowchart of shuttle launch. There was a very serious process of multiple layers of check of everything to make sure the shuttle is ready. Everything would be checked, even astronauts' health and everything, and everything that you can imagine will be checked by various committees. What I have put here is the check of the shuttle, the three components themselves, which includes the check of rocket boosters. In fact, the line, the red boxes are for the rocket booster. You can see solid rocket booster. This is the contractor, which was aware of O-ring problems. So let's start here. This is called level 4 check, which is really the lowest level. The fire call is here, and the fire call should check first everything and the O-rings and all the issues before the flight and certify it and say that, yeah, as far as we are concerned, the solid rocket booster, everything is a go. So that starts. Then that goes up to level 3. This is Marshall Space Flight Center, which is really NASA. And they were aware of the O-ring problems before the day of launch. So now we have the manufacturer, designer knows that the O-rings will not perform during cold weather. And NASA, that is responsible for rocket booster, knows. And then this information, this is very interesting. Then what happens is after level 4, it goes to level 3, and then level 3 sends information to level 2. This is very important, pre-flight readiness. This usually happens like 2 weeks before the flight. It used to happen. So this is now more serious committee in NASA that looks at everything again. And this group was not aware of O-ring problem because they were not told. This is disaster. This is communication, lack of communication, not sending off the data to people who have the responsibility of certifying the flight, and they're responsible for everything, and they check everything, and they ask all participants if your system is all certified, correct, flight ready, and that's why it's called pre-flight readiness review. 2 weeks before, let's check everything to see if shuttle is ready. But what didn't go to them was the problem of O-ring, the issue of cold. If the weather is cold, should we launch? So that's why I put this. Then the level 1, of course, is the flight readiness review of the highest level before it gets to mission management team, which has the final authority to certify, sign, and say that the flight can be done on January 20. But you can see the most important layers as it goes up are not aware of this problem. Lack of communication. It's a very serious problem. I'm sure, again, you would agree with me that you see it in your offices and your work, that this communication sometimes not as dramatic as this, right? So causes problem. So let's look at January 15 now. It's almost 2 weeks before the launch, and this is flight readiness review meeting. Okay, put yourself in that room. I put myself in that room to collect this information. Like, I'm curious. I want to see what happened. So the first pre-launch meeting was the level 1 flight readiness review meeting on January 15. This is the highest level, and they're checking everything. If they certify, it's a go until something happens that we should stop. It's very serious, and the meeting for certification. All attendees, these are the heads of various parts, like protocol liaison was there and all of that. And they confirmed that the NASA manager for all equipment and personal plans has certified them ready. In other words, the report to the head of this level one, the highest level was that everything is certified as ready. No mention of warranty. Participants were requested to identify any constraints that will stop the flight. Okay, now, exactly if you close your eyes and put yourself in that meeting, I put a blank room for you and think of, you're asked, you know, such and such, is your, booster ready? If there's any problem that you should tell us. No one brought up the repeated damage to O-rings during the previous shuttle flights to NASA. You saw from the beginning, there were damage, a lot of damage. To NASA's highest review and certification level. So what happens? What happened at that meeting was it was just to know that everything is good, and the review board certified that all elements of shuttle were deemed flight ready, and they sign up. Actually, it was signed the certificate, the flight certificate. All right. Then what happened was January 27 now. So actually, the flight was scheduled for 24 or something, and because of the weather and storm and a couple of times it was postponed. So now we are at January 27, what happened was Iran knew, again, you have to put yourself inside the meeting room, which I did to put these slides together. On January 27, around noon, NASA mission management team met, and after about half an hour of discussion, all voting members were polled on the feasibility of a launch within 24 hours, because it was also scheduled for 27, but they felt that, we can't do it. There was high wind. So they met around noon and said, okay, everyone agrees that we postpone it to tomorrow. And around noon, only half an hour later, the mission management team said that we are not going to launch this shuttle today. The wind is too high, so we are going to launch it tomorrow. And around 9:10 in the morning. All right. Still, none of the people who are deciding know about O-ring, including this mission management team. This is the high level. This is here. The highest level, which can actually stop the launch, even though it's certified on January 15th. They can stop it for any reason. So this is very high caliber. This highest caliber group, NASA mission management. You can scrub for anything. So they are meeting and they're planning for tomorrow. They have no idea about the O-rings and cold weather, right? Even 3 layers don't know, let alone the top layer. So what happens is, after they approve, now these are the hero engineers who come into play. Around 2:30 on January 27th. So what happened? 12:30, the highest group review team in NASA says that tomorrow they're going to launch it. At 2:30 Florida time, Tycall Utah plant, which is the place where all these engineers are for O-ring and everything else of product, they basically convened a meeting. Actually, it started with Robert Ebeling. Bob Ebeling, uh, after he's kind of like the senior engineer related to O-ring, and Roger Boisjolet on the right is the guy who is in charge of O-rings. He's holding some O-rings in his hand. So Ebeling, after learning that now they are going to launch Shuttle on 28, the day after. 27 to 30 is pretty close to tomorrow. So tomorrow they're going to launch it, and they're going to launch it at the low temperature. Had a meeting with Roger Boisjolet and other Tayakal engineers who were also involved, 4 or 5 of them involved with O-ring plant. And of course, all of them were concerned about the cold weather prediction, 26 degrees almost, and where the Challenger was waiting to be launched. All right. So what happens? Now this is 27. It's about 2:30, and Tayakal engineers, Ebeling calls a meeting, Utah, and what happened there? Ebeling actually told the commission, presidential commission, this. The meeting lasted 1 hour. Okay, it was 2:30, so the meeting lasted until 3:30. But the conclusion of that meeting was engineers were very adamant about their concerns on this lower temperature because we were way below our database. Remember 53 degrees. We are way below our database, and we were way below what we qualified for, because they also should qualify engineers at what condition you can use it. And the qualification was 50 degrees or so. So we are talking about now 26 degrees predicted. And of course, these engineers, knowing all the information and test results as well as performance from the past, they were very concerned. So this is what Ebeling told the commission. Later in the afternoon now, of course, nothing happened. So now Ebeling met with engineers, his colleagues, and everyone agrees this should not be done. This should not be launched. So Ebeling, of course, cannot rest. So he calls Alan McDonald. Alan McDonald was not engineer, but he was the liaison from, he was engineer, but he was not expert in this particular area. So he was the liaison of Tayakal on boosters in Miami, in Florida. Not in Florida, where Kennedy Space Center is there, and he's there to represent Tayakal and be in charge of issues related to rocket boosters. So Ebeling calls him, he's working for Tayakal, of course, McDonald, and Ebeling also, and expresses his concern. So the engineers are moving, they are very nervous, and tells him about the performance of O-rings or bad performance of O-rings under low temperature. So McDonald tells Ebeling that, of course, McDonald also agrees that this is serious. So tells him that just send me see, in those days, there was no email, there was no scanning, there was no, believe it or not, I've been there. Some of you may not believe this, but it was something called fax, if you know what fax was. So McDonald tells Ebeling that in Utah, McDonald is in Florida, near the Shuttle, and says that prepare the data that shows this, and I'm gonna get the meeting with NASA people so we can show them that with data that this cannot be done. This is not going to work. The cold weather is going to cause trouble. So, and then Ebeling, of course, goes to Boisjoly, who was in charge of all these charts, and says that prepare the charts and do it. And eventually they get to work, Boisjoly and Ebeling and Utah people, engineers, to prepare and fax the data on bad performance of O-rings to NASA and have a meeting, which happened the night of 27, just maybe 10 hours before the launch was done, between NASA and Tayakal. So now this is that meeting. Now the engineers for Tayakal, the O-ring people, O-ring engineers, are in Utah. The NASA people mostly are in Florida. So then there is a conference call. But in those days, there was no Zoom. So what is the conference call? Is used to call it teleconferencing. It was a telephone like this you see here, and everyone with wires and telephone lines, landlines. There was no wireless phone. They come in, they sit at different meeting rooms, and they just get connected with the phone. And this meeting started at about 9. In fact, until 9:30, the faxes, the details of joint data did not get to the meeting. So they started the actual meeting at 9:30 at night, the night before the lunch, almost 12 hours before the lunch, maybe 14 hours before. The O-ring engineers from Tyco were there, sitting there and having connection to the teleconference. And there, the top guy was Bob Lund. Lund was vice president of Tyco for engineering. So he was a top engineer in Tyco. And there were, of course, 3-4 other engineers who were in charge of O-ring, really. So this is the Tyco team in Utah. And the NASA team were director of launch, director of this, that, in Florida, responsible for making decisions on these things. So let's see what happens. When the teleconference started and kind of like everyone got the faxes and they could see the data, Bob Long, vice president of Tayakal, started the presentation. It was really on the phone, tell them, look at page 10, look at page 2, you see that curve. That was the way they were presenting. It wasn't PowerPoint. So what happened was he recommended at the meeting teleconference that we should not launch until the temperature is 53 degrees Fahrenheit. That is the data we have. That is the experience we have. That's established that we had a flight with 53 degrees, and it was damaged. 6 O-rings were damaged, right? But we can live it. So this was the lowest temperature that any shuttle has been launched and safely eaten. So at this point, the whole team, Paracol team, is opposing the launch, and he is saying that we should not launch until it's 53 degrees. The predicted 26 degrees will not do it. You should not launch, right? Looks very good. He's doing his job. Now what happens is this. NASA deputy director at Marshall Space Flight Center, the presidential commission has names. So I'm just moving with the quote. The NASA deputy director, pretty high level official, said at the meeting that I am appalled. He used the word appalled by Tayakal recommendation. that don't launch it unless temperature is 53 degrees or more. Another NASA, this is what was saying, another NASA project manager responded to Lon by saying, what do you want me to launch? When do you want me to launch? Next April? No, imagine, this is January, which means we have to wait until all the storm and everything is gone from Florida. This shows the feeling. Just put yourself at the meeting and see what's going on. Then at this point, Tayakal VP Land, seeing the reaction of NASA, stopped the meeting and asked for a private conversation with his engineers. Uh-oh, that's not good, right? Later in the interviews with the commission, he said that there was no pressure. And NASA said there was no pressure, but engineers said that definitely there was very high pressure in the room in Utah. That our vice president says that, okay, Vice President Payakal told NASA that why don't we stop the teleconference, mute it, as we say today, we're going to have a private caucus with my engineers. Payakal's private caucus started with the VP of engineering at the meeting saying that to engineers, now they are just themselves, only Payakal engineers. He tells them that, look, now this needs a management decision, not engineering. It's a management decision, which means with NASA reacting like that, the manager should make a decision. So all engineers at the caucus strongly opposed to launch. They always stayed that way. They never agreed, no matter what was going on. Until the end, they said that we should not launch. So what is Lon to do? He goes back to teleconference and presents a recommendation for the launch on January 28th. He told engineers that you don't say anything. That's pretty much saying that this is management decision. Don't say anything. I'm going to talk. He was talking anyway, but now you mentioned that this is management decision. I'm going to go back to the teleconference. And when he went, he told the NASA officials that he recommends now launch for January 20th. Of course, the engineers did not do it. No one was there, no secretary, nothing. So the recommendation to launch was handwritten on a notepad, and without any polling of those present, was faxed to NASA. So the engineers, in fact, I read somewhere that the engineers didn't know what he's going to say when they went back to teleconference. He said that this is a management decision. Let's go back to teleconference. He goes there and he says that we recommend now from Tayakal to launch tomorrow. And the recommendation was just scribbled on a notepad and was faxed to NASA in Florida. And then the engineers returned to teleconference and so forth, and the recommendation to launch was read at the teleconference. So that became kind of like the response of Tayakal to NASA on the question of launch. So at this point, the technical question had been answered. I tried to explain to you what happened, why. With all that evidence, the launch was approved by Tayakal and NASA. So this is a good time to take a quick break 5 minutes break, and when you come back, we'll continue the last part to see what are the ramifications of this in terms of code of ethics, where that is. Okay, so let's take 5 minutes, please, and come back, and we will continue from it. Okay. Please come back 27 minutes past the hour. It's now 22, so I'll come back 27 minutes past the hour. All right, welcome back. Now let's get to discussion of ethical issues and whether or not the violation of the code of ethics was the root cause of this tragedy. I believe it was. Let's see what you think. Of course, these are the six canons of uh, National Society of Professional Engineers Code of Ethics. They're all familiar, but the most important one is the first one, especially for this case, to hold safety paramount. Canon 1 also has, all canons have rules of practice, but this Canon 1 has rule of practice, and the one that's very important to me for this case is if engineers' judgment is overruled, like this case, under circumstances that endanger life or property, they shall notify their employer or client and such other authority as may be appropriate. This is very important. It's as important as holding safety paramount. This is the way you hold safety paramount, and if your boss is overruling you, you have to go to the authority and tell them that, look, this is what's happening. The other one, item D, is engineers having knowledge of any alleged violation of this code shall report thereon to appropriate professional bodies and, when relevant, also to public authorities, and cooperate with the proper authorities in furnishing such information or assistance as may be required. Basically, professional engineers, registered professional engineers, licensed, have a duty to report if they see any wrongdoing that they're aware, even if they're not involved in that, but they see that someone is doing something wrong, they have to report. There was a conflict of interest. In 1985, a year before the Challenger disaster, Morton Tackoff performed tests to evaluate the effects of temperature. This is amazing, right? This was after the 53 degrees range. So they started doing the tests. And the test said that at 100 degree Fahrenheit weather temperature, the O-rings maintained contact with the metal sealing surface, perfect, no problem. When the temperature was 75 degrees, the O-ring lost contact for 2.4 seconds. This is not good, but this is one of those damages that apparently some place was damaged and some putty filled it and so forth. Then, at 50 degrees, the O-ring did not reestablish contact in 10 minutes. It took 10 minutes. That's a lifetime for fuel to come out and do damage. 10 minutes, it wasn't closing the gap. At which time the test was terminated. I'm not going to say a word. You saw that your O-rings are not performing, and you just didn't continue the test. They should have done like 30 degrees now to see what happens. And of course, they would realize that it doesn't work and the launch will not be done. But what is really, for me, ethical issue is that Morton Tackoff was a designer and manufacturer of the solid rocket boosters. It concluded in-house tests of its product, which failed. Tackoff saw that its product is not performing and did not continue the testing. And it stopped the test and did not establish a minimum temperature for launch. I put it kind of like mildly. Independent verification could strengthen confidence in the results. But you have, I'm sure, your own feeling of what this means, that you do a test of your own uh, product in your own basement, it doesn't show good results, and you just don't test it further. You remember the teleconference at 9 p.m. teleconference, the night of January 27, managers were asking tire call engineers to prove that the O-rings are unsafe in low temperature. Instead of the pass criteria, which is really the criteria in all operations that we usually have, that tire call was only to prove that the system is safe. You know better than I do. You're in trenches more than I am. How can you prove that something is unsafe? That's very hard. It's almost impossible. Unsafe, unless it's so bad that it is obvious, of course. But proving unsafe is not the case. The engineers only should prove safe. Even definition of safe is embedded in our system, that if you follow the code, that is definition of safe. Because that's why the code, you have done what you should do to make the system safe. So safe is not scientific engineering rule, it's public rule. To us, safety means what? Means I should follow the code and do design to satisfy the government code. Uh, Now, imagine you are the technical engineer using limited data on past performance of O-rings, very little information on the cold temperatures, and non-existent reliable test results. Of course, tests stopped at 50 degrees. Technical engineers could not meet NASA's requested burden of proof to prove that for 26 degrees, it's going to be unsafe. We don't know. We didn't test it. Then at the same 9 o'clock teleconference, you remember the night before lunch, Tarkal and NASA manager ignored the engineer's objection to launch Challenger the next morning. Tarkal VP himself, an engineer, first sided with engineers, as I told you, and opposed the launch, but then asked engineers to approve the launch, which they refused. The actions of Tarkal vice president certainly appears to be inconsistent with the Canon 1 of Code of Ethics, which says engineers should hold paramount the safety, health, and welfare of the public. Is asking an engineer, this is a good question, is asking an engineer to perform an impossible task inconsistent with the Code of Ethics? I'm not using the word in violation, it's too strong. Is it inconsistent to ask your, colleague or your engineer, junior engineer, to do something that's impossible to do? Are you, as licensed engineer, violating the code by doing? Well, the answer is not easy. I couldn't find really, in my experience, maybe you have a better idea of being influential. What is the answer? But consider these points. Engineers are obligated to hold safety paramount. So if your request is not holding safety paramount, certainly it's not good. It could be in violation of code of ethics. The code of ethics emphasizes integrity and honesty in professional practice. So certainly the question of NASA was a little bit, I'm not going to accuse anyone of any wrong thing. I don't have that right. It's not right. I cannot proceed. All I'm saying is that sharing my feeling with you, I'm sure you have also your feeling. It's really unfortunate that these kind of webinars are not interactive in person. I can see you, you can say something. But that's really a drawback. It's really bad. But you're hearing me and you're thinking, you have your feeling about what NASA was doing, and certainly mm, code of ethics or not, it's not fair to do that. Engineers also have a duty to report unethical practice or pressures that are the pressure is such that it's clearly violating code of ethics, violating safety is paramount, and lives can be lost. Then you have the tool of going to authorities. Now, NASA's flawed decision making. Presidential Commission said that with regard to this process I mentioned to you, that communication, the main people who decide level 1, level 2, and the mission management people, really is like level 0, where the buck stops. They have no idea what was going on with Odin. So Commission said that NASA's flawed communication allowed launch safety concerns to be bypassed by key decision makers, specifically ignoring engineers' warnings about the behavior of Odins. Again, I'm sure you are thinking, if I have this, yeah, sure, I have to make sure everyone gets the serious information that I have. Then the Presidential Commission also added that with regard to management in NASA, the normalization of evidence, the deviance was there. NASA and contractor Martin Paikal had normalized the erosion of O-rings in previous flights, treating a dangerous design flaw as acceptable. That's the meaning of normalization of deviance, which made the accident rooted in history. In other words, the accident was not just suddenly, no warning happened. It was building up. It had its roots in 25 years of performance of Owens. Broken safety culture. This is really directly related to safety paramount. In NASA, apparently, and as Commission also said, safety was not paramount. The cost was paramount, cost saving. Inadequate oversight. The Marshall Space Flight Center, this is the center in charge of flight, failed to properly manage the shuttle program components, leading to a breakdown in quality control. This is problem of really quality control, quality assurance, right? What is normalization of deviance? When I heard that the first time, it's really referring to a gradual acceptance of lower safety standards in organizations. So the things are happening so often, and they're wrong, they're not good, but they're not really causing catastrophe, and you just accept it until they do. Initially, small deviation from established norms may seem harmless. This is minor damage to O-rings. Over time, these deviations become routine, so you accept damage once in a while, and are no longer questions. It's just a statistic. Did we have damage this time? Yeah, we had two O-rings damaged. This can lead to increased risk and potential disasters in critical situations, like this case. So the last part, what should a PE actually do in a situation like this? Not that I know, I'm like you know, I always actually prepare these slides, always, every minute thinking that I am attending, like you, and I want the person who's giving the webinar do the same thing I would do, go find things that I am interested. So, of course, you got the information on the system, you got the information on decision to launch, and you got the information on all these, not good looking ethical behavior. And you might think that, what do I do now if I get into the same situation? So I tried to give you a few items. Uh, of course, the most important one is your moral and ethical behavior compass. But as far as, tools that are available to us to avoid this, uh, I try to put together as I would do for myself to figure out what I'm going to do. So, first of all, uh, this book by Wanda Paul and Riakers has a very good section on applying engineering ethics rules at design level. That's what many of us do, right? So I found this very good. So most of it is really a quote from that book. I usually mention at the beginning, but it's not too late. I'm not ethicist. I'm not an expert in ethics. I'm like you, and I'm interested, as you are, by attending this course. It's clear you are interested in making sure you learn as much as you like on ethics and follow it. So we are all the same, concerned about making sure we do uh, behave ethically. And in this case, it has to happen from beginning of design. Then he says that the design is problem analysis and formulation, definition of problem, conceptual design, right? Simulation of your design to see how it performs. Then decisions to change this, to change that. And then detailed design. So now you're getting to nuts and bolts. Then prototype developments and testing, like cars, you do crash testing and so forth. So with that, the authors further state that at each stage of design, you can uh, think of uh, ethical questions, and the most important to me and all of you, I'm sure, is holding safety paramount. So holding safety paramount is every minute of design in our minds, right? Then, as far as problem as a formulation, I'm just applying it to this shuttle situation. That objective of space shuttle program was to design and build a system of reusable spacecraft to carry 5 to 7 astronauts and 50,000 pounds of load. So as soon as the word 5 to 7 crew comes, then immediately holding safety paramount is that. It's the first priority, and maybe there is no second and third. Maybe fifth priority is, if I can make it cost efficient, I should try. Conceptual design. Now, in this case, initial concepts for shuttle, actually, I'm showing it here on the right. All kind of changing, but this is concept. The initial concept plan was to launch it vertically as a rocket with additional booster rockets adding to the lift-off thrust and land it as glider horizontally. So that was the requirement of the climb. So at that stage, you gotta think of going up vertical. It can tolerate forces and so forth. Safety is there, and coming back to be horizontal and land. Again, it can do it safely, and that is the Columbia disaster. So it paid actually in both cases, going up and coming down. No, safety is paramount, was first priority. Simulation, of course, testing. I couldn't find any testing, and as I said, the only testing they did was going in wrong direction, and then they just stopped it. That's not the way you put safety first in your design. Simulation, these days we don't need to do tests. Crash tests now, you do 100 analysis, and only one last one usually is required by federal government to do the actual physical test. So they could do all kind of analysis. Even in those days, we had pretty good tools for analysis without expensive tests. So decision. The decision to use the specific material and detail in the O-ring without necessarily realistic testing or analysis even. Just computer analysis is very cheap these days. And reliable data to find out what will happen if we go to 26 degrees was not done. So the decision was just flawed. And the detailed design, of course, during the detailed design phase, it's even more important to keep in mind holding safety paramount, right? What do we say, or what do we are told? The devil is in the detail. So working in detail for as long as I did, and many of you, you know, what can happen is the detail, little detail. Prototype development, the same thing. You gotta keep in mind that in order to hold safety paramount, you gotta do analysis, you gotta look at everything, at least simulate it with computers, and they didn't. Groupthink, this is a very important item. Groupthink happened here, of course, right? The meeting, it happens all the time. I'm sure many of you have seen it in your feed. That just people are not gonna stand up. It's just we are shy of standing up and as they say, rocking the boat, right? It's very natural, but it can have very serious consequences in our world that we are dealing with safety. Almost all of us in engineering, even computer engineering, they develop all these tools for healthcare, this, that. In developing the tools, they should be careful and hold safety paramount that no one in the hospital suddenly ends up with malfunctioning of software, the bots. So groupthink occurs when people go along with the group's decision rather than making the best choices. This is going on. Under the table, they are saying, no, no, we are doomed. No, bad idea. But they are not going to bring it to the room. They say, oh, yeah. So do we agree? And the boss asks. And everyone says, yes, yes, I agree. Yes, yes. This is good. Why do people go along with groupthink? To maintain loyalty, right? I'm sure you feel on the other end. Yeah, you have to be, respecting your boss. To prevent expulsion from the group, a good word for being fired. To prevent losing their job, or to avoid stressful situations. According to Irving Janis, he's very respected psychologist. And by the way, most of these things are directly taken with this site. It's very, very important site at the University of Texas. So groupthink is a deterioration of mental efficiency, reality testing, and moral judgment that results from in-group pressure. So you kind of switch off your own responsibility and mental efficiency to make the right decision, not the decision that everyone else wants or your boss wants. Groups may also reach decisions including moral judgment, which are more extreme than any single member of group originally supported. It's very important that we recognize this, that when we are in a group, we go along easier than if we were alone in our office or home. No, I'm not going to do that. But everyone is doing it. That is the group think. Unfortunately, if group think takes hold, group members may not even question ethically dubious decisions and actions. It becomes, again, another form of normalization of deviant in terms of thinking that everyone says this is right, all right, we go with it. For example, some people say that the Bush administration's decision to invade Iraq because of non-existent weapons of mass destruction was due to groupthink. Of course, as I mentioned, this is all code. You can see it's all directly code, so I don't get into politics in this webinars. We are engineers, we just want to spend our time on engineering items. But this was the example we had. Indeed, groupthink can cause us to value harmony and consensus. It seems that how to avoid groupthink, this is important. It seems that the team leader is the most important individual for preventing groupthink within a team or at a team meeting. Some suggestions are this. Don't have groupthink. You can evaluate all ideas critically, especially for the group leader. As a group leader, keep your ideas to yourself at first. Have small group discussions. Consider an outsider's opinion and have a devil's advocate. I really believe in it. After so many years of professional meetings attending and faculty meetings and all kind of the other meetings, you gotta have a devil's advocate. Unfortunately, if group thing takes hold, group members may not even question ethically these decisions and actions. So I have this one actually. Now, one other item is whistleblowing. Experts from National Society of Professional Engineering Code of Ethics. You saw this before. If engineer's judgment is overruled, you have to report. Engineers knowing some wrongdoing, you should report it. Okay, so these two things are taken from that. Now, whistleblowers do that action. Whistleblower is someone who reports waste, fraud, abuse, corruption, or dangers to public health and safety to someone who is in the position to rectify the wrongdoing. This is the A whistleblower typically works inside, but that doesn't mean that always a whistleblower is really an insider. Then what matters is that the individual knows something and says something. Knows something wrong and says something to the authority that should know about that thing. This is a very noble thing. Very noble thing. And now the federal and states have protection of whistleblowers against retaliation. There is an Inspector General website of the US federal government, and they define whistleblower. It's almost the same as I had before. Then what is protected disclosure? You can, if any violation of any law, rule, or regulation, if gross mismanagement in federal government, if gross waste of funds in federal public entities, it's not just federal, abuse of authority, or substantial and specific danger to public health or safety. I wish this was listed first, but I'm not the Inspector General. He or she has put office. I mean, the office has put this at the end, but this is really the beginning. But of course, governments are to uphold the law, so they put the law to the beginning. Then, as I said, the retaliation is defined and this, that. So I'll just leave it at that you have protection. The laws will protect you. And even most government entities have a online place that you can go there, click the button, and you don't need to give your name or information, nothing. They give you a number, that's your code for your identity, and you can go back with that code and see what happened to what you said. You can only say what you think happened, and that's it. They will investigate if it happened, they will take care of it and correct it if it didn't. It was just your concern and you express yourself to government, and that's okay. Then the last thing is the important concept of preventive ethics. Professor Harris, in 1995, he was a professor at Texas A&M, and he defined this preventive ethics. What he means is this. the disasters like this one occurs, either bad engineering, which was the case here, bad management, which was the case here, and bad ethics, which was the case here. He's putting it as or, but I'm saying that in this case it was and. It was and. But even if it's or, he then continues saying that we usually go and investigate bad uh, engineering causing disaster. I do that after earthquakes, go to earthquake sites. I do failure analysis of bridges after collapse. I testify to court, and all of this we do to learn from past collapses to start developing information that can prevent it. Bad management, the same. You look at Enron, this, that, all these bad managers, even NASA, and try to learn and develop rules for better management. What Professor Harris said is that preventive uh, ethics is to do exactly the same and look at the cases that ethics was the core of disaster, like the Shuttle one, and discuss it with your fellow people who are involved, like I'm discussing with you, your peers, we do the design and this, that, and together try to come up with how we can, you and I can prevent it. And he said that this is as important as going after earthquakes and learning from earthquakes. So this was actually what I tried to do in this webinar, as Professor Harris says, that we should do investigation of bad management, investigation of bad engineering, and investigation of bad ethics. And that's exactly what I tried to do in this webinar. And with that, I will leave you with this one conclusion. The only conclusion I have is that if only NASA and higher call managers had listened to those engineers with knowledge and high ethics and were serious in holding safety paramount, one word, holding safety paramount in their decision making, this man-made catastrophe would have been prevented. With that, I appreciate your 2 hours registration fee and spending the time with me. I hope that you have question and answers now and comments. So I'll go with that. Let me bring the QA. Let me see if we have uh, I'm gonna see if we have here any chat. Let me open the chat. No here. QA. No questions. So if you don't have any questions, if you have questions later, my email is astane, ASTANEH, at Berkeley, BERKLEY.edu. I'll be happy to answer it. You send it to me. And with that, I will end this webinar and wish you the best. We are at 2 o'clock exactly, so best wishes for your health, your loved ones' health, and success in doing those wonderful, safe, and efficient structures. Thank you. Let me see if there is some question. Thank you. This is the end of webinar. No, I think we don't have any questions. So goodbye, and hope to see you in other places and my other webinars. Best of luck. Thank you. Not having any questions, this webinar is concluded. Thank you again.